G'day viewers. In this segment I'll talk about traffic shaping. Traffic shaping is about constraining the flow of traffic both in terms of parameters such as the average rate or bandwidth it needs, as well as other parameters such as burstiness. And it's particularly useful in quality of service because constraining traffic can help the network make good on any promises it makes. In this segment we're going to look at token buckets, a particular kind of traffic shaper which are widely used as a key building block for quality of service. Okay, so a little motivation first. So traffic shaping is about constraining traffic flows in terms of their properties, or really the load which traffic flows which come from users or applications can place on the network. We can limit them in a couple of ways. Just limiting the total amount of traffic by shaping it enables us to make bandwidth guarantees, because if we shape traffic, we can control how much traffic is in the network, and that way we can be sure that we'll meet the promise about so-and-so having a certain level of bandwidth. We can also limit not only the average rate of traffic, but also the burstiness. Limiting the bursts of traffic helps us to be able to avoid unnecessary queuing and loss within the network. So again, it can be useful for quality of service. The big question though is how we should actually go about shaping traffic. From the network's point of view, it might be desirable for traffic to be as smooth as possible, because that way we'll avoid unnecessary bursts and loss as queues fill up. But on the other hand, if you think about real apps generate varying traffic. They just do. As you surf the web, or as you use a remote desktop or something, or as media is compressed in different ways, the traffic that's sent into the network is often quite variable. So it's unrealistic to think that applications will smooth out their traffic. Here's a little bit of motivation just to understand the differences between patterns of traffic that applications might inject into the network. This graph shows the bandwidth on the y-axis versus time on the x-axis. And there are two flows shown just to show very different behavior that they might exhibit. Flow A is a good old smooth flow. It sends steadily at a rate of 1 megabit per second over a period of 3.5 seconds. Flow B, on the other hand, sends at a low rate and then occasionally shoots up and sends at a high rate. Then back down, and then occasionally it shoots up again. Now, Flow A and Flow B clearly have very different behavior as far as the network is concerned. But they actually have the same average rate, which is 1 megabit per second. So we can see from this example that the average rate alone is not a good descriptor of behavior in terms of what the network can expect from traffic flows. So how should we go about describing traffic flows to the network? Well, what we'll do is constrain two parameters. We're going to constrain the average rate because this matters in a long-term sense. It relates to the amount of bandwidth or capacity that's needed in a network. To carry both of these flows, we need to allow for a megabit per second for them within the network over a longer period of time. We'll also want to describe or constrain the burstiness of the different flows. Flow B is harder to carry in a sense with only 1 megabit per second of network bandwidth, because when it's above it, it's sending bursts into the network which will end up in queues somewhere, causing delay and potentially loss. So we might want to limit the burstiness, or at least know how big it is so we can handle it. However, simply using these two characteristics rather than the average is already very useful. The two characteristics are much more expressive than the average because they allow a variety of different flow patterns to be characterized and distinguished. On the other hand, these two characteristics, we've gone from 1 to 2, it's still a relatively simple model for the network to work with compared to all of the infinite variety of traffic patterns that could be sent into the network. So without further ado, let's go to the RB token bucket. The token bucket is a traffic shaper which has two parameters, that's the R and the B, to constrain the traffic. And the R and B constrain the traffic as follows. The R parameter constrains the flow of traffic to have an average rate of no more than R bits per second. The B parameter constrains the traffic to have instantaneous bursts or traffic that is injected into the network over and above the average rate, the long-term rate of R, bursts of no more than B bits. So that's the limit on the instantaneous load which can be placed on the network by the traffic flow. Now we have this picture here of the bucket. So a token bucket is usually explained in terms of a bucket analogy. So here it is, and I've changed the writing here to reflect the bucket analogy. To implement a token bucket, think of having a bucket with capacity or size B bits. That's how much water or how many tokens or credits it can hold. The bucket has been filled up by a tap that runs at a rate of R bits per second. That's how quickly water or tokens or credits are going into the bucket. The way you then use the token bucket is when you want to send, to be able to send, you need to be able to remove tokens from the bucket or draw that amount of water out of the bucket. If you want to have a packet to send and there's enough water in the bucket, you take it out and you're able to send the packet on its way. If there's no water in the bucket, however, you can't send the packet. It's outside of the token bucket specification, so the traffic is not constrained according to a token bucket. Token buckets are useful because they're able to constrain the greatest or largest amount of traffic from an RB source that the network can expect over time. So let's just imagine that we have traffic that's coming from an RB token bucket source. What kind of traffic could that impose on the network? Well, we do know something about it from the R and B parameters. This line here, sorry, let me draw that again, this line here, this is meant to be R times time. This is the long-term rate, maybe that's a little better, over time. So it's just as time goes by, it's going up at a rate R. This is the average rate, so we expect traffic to go into the network this fast over time. Now at any particular time, the traffic could burst and it could send B bits over and above that long-term rate. Of course, it can't send two bursts back to back and go even higher. If it bursts, it's going to have to wait for a while until it gets back down so that it's sending no faster than the average rate. But if we add the bursts together, we have an upper line, which is RT plus B. That line indicates the maximum load that this traffic could place on the network. The real traffic might go something like this. You can see the traffic went along at its rate for a little while, and then suddenly around here it crept up fairly quickly. So it was sending faster than the average over a short period of time, and it sent quite a lot of traffic into the network and got near the upper line. Then it had to send slowly, more slowly than the rate, and do pretty much nothing for a while until it got back down closer to its long-term rate. So an RB token bucket source is constraining the traffic that an application can send into the network. And here's that picture cleaned up, just so that you can work through it a little more clearly. Okay, so that is an RB token bucket. A token buckets can be used in two different ways. They can either be used for shaping or policing. Shaping is about modifying the traffic near a source. So that's the traffic that's injected into the network. We can shape it to fit within an RB token bucket profile. The way we do it is as follows. We run the RB token bucket at the source, and as packets are generated at the source, we pass the packets as they're generated into the network when there are tokens in the bucket that we can use to send them. However, if we have a packet that's generated and we have no tokens in the bucket, then we have to delay or queue the packets at the source until our token bucket has more tokens, and we can then use these tokens and send the packet into the network. In this way, the token bucket is able to let the user condition their traffic to meet some kind of contract that's been agreed between the user and the network as to how much traffic the network will handle well. Policing is a different usage for a token bucket. Policing is something which is done within the network, within the edge of the network or at a network boundary. And it's done to verify that a source of traffic that's come from a user meets an RB token bucket profile. So we do it as follows. At a network edge device, this might be a router inside the network, we run the RB token bucket. And as traffic comes through, we meter or charge that traffic by taking tokens out of the token bucket that corresponds to the traffic. And if there are tokens there, then we let the traffic into the network. The traffic is in profile. On the other hand, if traffic is trying to come into the network and there is no tokens in our token bucket to fit it in, then that traffic is out of profile. And the network might do something nasty to it. The network might demote or discard the packets. Discarding is just throwing them away. They were out of profile. They were beyond what was agreed for an RB token bucket. Demoting is something that can be used in a quality of service scenario. We might have these packets which correspond to an RB token bucket. They might be a video call, and we might mark them as high priority, make sure they don't get lost and get them through. Anything in excess of the RB token bucket profile might be demoted by being marked as purely best effort. The network will let it through if there happens to be bandwidth at that time, otherwise it will get dropped. So it won't be treated as well. It will be demoted. But a token bucket used for policing lets the network check the traffic that comes in to verify that it meets a contract which has been agreed by the user, and to separate out anything in excess of that contract, so it can decide what traffic to treat well and what traffic to does not need to be treated well. Okay, so that's token buckets. We've seen how token buckets can constrain traffic. This can help both the user and the network. The network is able to limit the traffic that's coming into it so that it can meet any promises about preferential treatment for some kinds of traffic. And the user is still able to inject a wide range of traffic. It can flexibly make traffic while still conforming to some RB token bucket. The token buckets themselves don't provide any kind of differentiation or quality of service to traffic. That kind of differentiation, to handle some packets well so they go ahead of other packets, is going to require special treatment at routers within the network. And that special treatment will be provided with building blocks such as weighted fair queuing. In the following segments, we'll look at how to put together token buckets and weighted fair queuing to implement quality of service solutions.